Hi all, welcome back. So today we are solving the one more question asked in the ECE GATE exam. So this series is going to helpful to understand the concepts frequently asked in the control system. Yeah, so let us start. So this question asks about I'm just reading the question for the control system shown in the figure. The transfer function of the plant GS equal to 1 by s plus 1 into s plus 2 is connected to the compensator. So this is a compensator. So this is a k into s plus alpha. So here k and alpha is positive real values. So this is a k greater than 0, alpha is also greater than 0, and this is real, no imaginary. And which of the following pairs k and alpha represent the correct values of the closed loop system to have poles at -3 plus minus j root 5. So this is a closed loop poles location. So so you know this compensator is a PD controller, right? So the design the controller PD controller for this given plant to getting these poles. So this like pole placement techniques basically we are using here. So here so before to solve this question very simple. How we can solve this question? Like we know the poles, right? And Cartesian equations, we can know this Cartesian equation and just compare to this Cartesian equation for this and then find out the our alpha and k value, right? So before to that, let us go through the concepts related to this type of questions. So like this is our standard transfer second order transfer function. So generally here DC gain is 1, generally we put k is 1 here, right? So for generally you put k here, and when you put s equal to 0 we will get k is equal to 1, right? So natural frequency omega n, this is a natural frequency omega n radian per second, and damping ratio determine the nature of the tangent response here. So coefficient of the S is 2 zeta omega n. So this 2 zeta omega n, right? And constant term is omega n square. So generally in GATE question, the pole placement problem focus mainly on the denominator, means characteristic polynomial, polynomial, yeah. Okay, so generally we bother about the pole. So this is our standard Cartesian equations, right? This one, and poles are the, so when we solve this question, this equation, you will get this poles, right? So minus zeta omega n plus minus j omega n under root 1 minus zeta square. So we know that this is a standard equation, so usually we can find out minus zeta omega n, and the controls real part is responsible for rate of decay. This tells about the rate of decay, right? Because it coming either power minus zeta omega n or something, so it tells about the decay rate. All right, and imaginary part omega d is equal to under root omega n under root 1 minus zeta square. So this controls the oscillation frequency. So imaginary part tells about the oscillation frequency, and real part tells about the rate of decay, right? So pole's location determine the transient response of the system. This is very important. Sometimes the MSQ question there. So what's pole location responsible for this? So you just tell about that this is responsible for the transient response of system. So useful form like minus sigma plus minus zeta and j omega d. So omega d is a damping frequency, omega n under root 1 minus zeta square. All right. So here x dot is equal to ax plus bu and is equal to minus kx. So this like I'm just stating the pole placement technique also for this question is given question is simple. For this not necessary to that, but we should know the related concepts for these given questions. Okay. So generally they given the state space also. So here you we know minus kx like state feedback control. They can also find out this question. So u is equal to minus kx. So here k is equal to this again is a proportional controller basically k1 k2, and you just put this here. You will get a minus b kx. So this is a state matrix basically going to change. So pole placement, I mean pole placement also going to change, right? So this is a closed loop system matrix. So we have to choose the case such that eigenvalues of this means poles should be equal to desired poles, right? So that's a way we have to do that. So for this given question not necessary actually. So closed loop equation is we need to find out this a minus bk determinant, right, to be 0. So we'll get like that. So like second order we are just assuming this is like polynomial equation. So s square a1 k into s plus a naught k equal to 0, right? So just you compare it this our standard result polynomial, and you will get this like k1 k equal to 2 zeta omega n and not k in square equal to omega n square, right? So important to get pole placements performed by the matching the characteristic polynomial coefficients. So this is very important, right? So if you know these things, easily we can solve this type of questions. So sometimes they like x dot double dot plus. So this like we just convert to derivative form, differential form. So x double dot plus a1 x dot plus a naught x is equal to bu. So here similarly we just find out formulated in state space. So basically we just trying to understand from the given state space how we can solve this actually. Okay. So this is our closed loop polynomial equation. So becomes Curtis polynomial. Okay. So this is like we are calling polynomial. But when we put the 0 here, this is called the polynomial characteristic equation actually, right? This characteristic equation when you put the 0. But if you don't put the 0, this is called the characteristic polynomial, right? So this is no, not to worry about it. So like compare, when we compare this actually, so we'll get this a not b no actually. So we just need to find out this value k1 k2, right? So this is like a way we can find out identify desired pole. We know p1 p2, this already given our given question, right? So how we can do that? Find the actual polynomial, right? So compare the our coefficient. So sometimes they given not they given the transfer function, they given in terms of state space also, right? So in this we can also find out, right? So we can find out the k1, this is here k1 and k2. So like that we just find out the desired pole. You know the our natural frequency under root a square plus b square, right? And zeta we also know a square and by under root a square plus b square. So omega d is equal to b. So easily we can find out. So if poles are directly given, you can immediately obtain the omega zeta n and desired characteristic polynomial. Okay, so this is not needed, but I am still explaining to you. P over so like e power minus pi zeta by under root minus zeta square. This is standard equation they given. So this is 2% by uncertain time 4 by zeta omega n, and 5% I think 3 by zeta omega n. Okay. So damping natural frequency omega n under root 1 minus zeta square. So performance, like it comes to like performance requirement, they given desired poles we want and desired Curtis equation and to the match coefficient comparing. Just we are comparing the polynomial Curtis polynomial, right? So that's a scenario there. So you just pole placement equal to control the system dynamics by controlling the closed loop poles, right? So let us solve this question. So what's the question they given? Let us we go back and then yeah. So this is a 1 by s plus 1 into s plus 2 and this is a k into s plus alpha and minus 3 plus minus j. Okay. So here question is very simple. So this is a s plus 1 s plus 2. Here they put the controller and compensator they are telling actually. They are calling compensator, but this is a form of the PD controller. Okay. So unity feedback there, right? So here controller is this is output we can say. So controller they put a k into s plus alpha and our desired poles is minus 3 plus minus under root 5j. So we just find out the our this minus zeta omega n plus minus under root omega d. You can compare it for this. We know the standard equation, right? Otherwise we can compare, like let us solve this also if you don't know this actually. So what we can do, so let us check this value again. Minus 3 plus minus j root 5, right? Yeah. So what is our closed loop characteristic polynomial? Closed loop characteristic polynomial is s minus 3, right? And s minus, so this is a plus, we are doing one more pole like s minus p1 into s minus p2, right? So this we are doing actually here. So minus 3 minus root 5 j. So s plus 3 plus 3 plus root 5, right? So this will be, can say s plus 3 whole square minus root 5j whole square. So it coming out s square plus 9 plus 6s, and this is a 5 minus plus. So basically you get s square plus 6x plus 14. This is characteristic equation to the loop, right? So what is the actual in our block diagram? So this is a k s plus alpha into right, this is our gs and right. So this is a, so how much will be, right? So this will be 2s 3s plus 2 plus ks plus k alpha. So square 3 plus k into s plus 2 plus k alpha, and then compare it, 3 plus k equal to, go back, you will get 6, right? So k will get 3 and 2 plus k alpha, here you will get 14 I think, right? Is it correct, right? 14. So k alpha 14 minus 2 will give 12, and alpha we want 12 by k is 3, will get 4. So the 3 comma 4 alpha k and alpha. Let's go back to and check the option. So 3 4. So this is the answer actually, right? So hope you understood this question. So this question related about the pole placement, right? So we know we want to know pole placements. So closed loop. So basically, so we need to design a compensator such that uh, we should locate, I mean change to pole from the given poles like s minus 1 and 2 to this position, right? So that's all. And this question was very simple. Just we need to compare the given second order characteristic polynomial, and we find the solution, right? I mean find solve the questions. Okay, so that's all for this question. This I think hope you understood. Yeah, that's all.